This is Lecture 7, Reputation as an Enforcement Mechanism for Credibility. Let's just recap on Lectures 5 and 6. In Lecture 5, we looked at two different policy arrangements, one being discretion and one being commitment. We noted that commitment had a better inflation outcome, but there was an issue of credibility. So in Lecture 6, we looked at the issue of credibility or enforcement mechanisms with credibility in mind. We looked at the case of the fixed exchange rate regime and also the case of the fixed rule with an escape clause, so that we could overcome the problem of credibility, but there were costs associated with that mechanism. So of course we've looked at static cases with one period outcomes and decisions, but what we have not done is look at the dynamic relationship between the rational agents, the private agents, and the policymaker, because obviously that makes a difference in terms of credibility. If somebody has a reputation, then this gives them credibility. This credibility itself then becomes a cost or an enforcement mechanism. Let's consider the case where the public expect prices to rise in the future. In other words, future expected inflation has increased. We know by the aggregate supply equation that this will cause some negative effect on output. And the intuition behind that is that higher expected prices lead to actual increases in costs for the firms, where private agents push for higher wages. So for a policymaker, there is a trade-off. The policymaker can use this fact provided to us by the aggregate supply relation, that a positive price surprise will increase aggregate supply, but the policymaker also knows there's a cost associated with that for the following period. So increasing inflation on purpose, the policymaker increasing inflation can bring about a positive outcome in the current period, but in the following period we can end up with higher expected inflation and some negative effect on aggregate supply, as aggregate supply is reduced or shifts left. So this is a trade-off for the policymaker. If they use unexpected inflation, then there may be higher expected inflation in the future. So the policymaker has a choice. He can maintain his reputation, or he can use his reputation for one period only and have some loss to himself, which is the loss of this reputation. So the interaction between the policymaker and the private agents becomes a game. So long as the policymaker behaves, then the reputation is maintained, but as soon as there is misbehavior, then the reputation is lost. So in effect, we can look at how we can use reputation as a substitute for commitment, or in other words, use it as an enforcement mechanism in the objective of sustaining a low equilibrium inflation rate. Assumptions of the model are as follows. We imagine that the economy can be modeled as an infinite number of interactions between policymaker and the rational private agents. Private agents are assumed to have complete information part of the model, policymakers' objectives, objection function, all these kinds of things. So in other words, they are rational agents. And the aim of the policymaker is to minimize the discounted present value of the infinite horizon loss, of the loss over the infinite horizon, this endless interaction between policymaker and public. And to simplify matters, we have no stochastic shocks, so we set the shock variable in the previous lectures 5 and 6, V, equal to 0. So the model is a value function, and the value of the losses over the horizon. V is equal to the loss in period 0 plus the loss in period 1 discounted by 1 plus the interest rate, or where we think of R as the discount factor. So it would be smaller, the weight of L1 is less than L2 by the factor of 1 over 1 plus R. And as we go through the periods, we see that the discounting becomes greater in each period, but the losses are still all added together. So the value of the loss over the infinite time horizon is LT divided by 1 plus R to the T. Each individual loss in each period is given in a form that you'll recognize, only this time with time subscripts. The loss in period T is equal to half the output gap, so we know the gap between output and its target rate squared, plus half lambda times the inflation rate squared in period T. And as before, the constraint for the economy is set by the aggregate supply relation. Yt is equal to y bar, the natural rate of output, plus pi t minus pi et. So this is the difference between actual inflation and expected inflation in each period. Now remember the discretionary equilibrium. In the absence of supply shocks, inflation inflation under discretion will be equal to K over lambda, that's the inflation bias, positive inflation, and output under discretion Yd will be equal to Y bar, so output will be around its natural rate. Also remember that the expected loss under discretion is half times 1 plus lambda over lambda times K squared. Remember here that K is the amount that the policymaker wants to keep output above its natural rate, and the higher the policymaker wishes output to be, obviously the higher the losses to society in terms of inflation. Remember that under the fixed rule we had the enforcement mechanism of the pegged exchange rate, that the expectation of pi was equal to the foreign rate of inflation, which we assume to be 0. So here we can just say that pi t is going to be whatever it was in the foreign country, or to the pegged country, pi r, and y was equal to y bar minus v. And in the absence of shocks, that y is equal to y bar. So we can substitute those two, equation 6 into the loss function, equation 2, to get the expected loss under the fixed rule. So the expected loss under the fixed rule is going to be equal to k squared over 2 plus lambda over 2 pi squared, where pi here is the inflation rate under the fixed rule. Now consider the case where the policymaker has committed, the public have formed expectations But instead of carrying out the commitment, the policymaker reneges and instead sets inflation at a loss minimizing rate. And remember that the expectation of inflation currently is equal to the inflation rate under the fixed rule. And in our example before we had that was equal to 0. So the public have been duped. They're expecting low inflation, but instead the policymaker sets it to the loss minimizing rate. So inflation under cheating, pi c, is going to be equal to k plus pi r over 1 plus lambda. And this is the optimal inflation rate under pure discretion without shocks, and we see the explanation here. And output under cheating will be equal to y bar plus k minus lambda pi r divided by 1 plus lambda, which is optimal output under discretion with the shock set to 0. If we substitute optimal inflation and output under cheating into the loss function and take expectations, we have the 1 period expected loss. Loss is under cheating. ELC is equal to half times lambda over 1 plus lambda multiplied by pi r plus k all squared. This is the macro outcome where the policymaker commits to the fixed rule, the public form their expectations of inflation as per the fixed rule, but the policymaker then cheats and creates higher inflation. So this unanticipated inflation via the aggregate supply equation will raise output of its long run rate, and this is the cheating outcome. The key point here is that the expected loss from cheating is lower than the commitment to a fixed rule, and we'll see this going ahead. The incentive for the policymaker to cheat is given by a function that we can call temptation. The temptation of cheating, T pi r, is equal to the difference between the expected losses for the fixed rule and the cheating outcomes. So if the expected losses under cheating, ELC, are less than that under the fixed rule, then there is a positive temptation for the policymaker to cheat. In fact, we can write out the difference between the two expected losses under fixed rule and cheating as T pi r is equal to half times 1 over 1 plus lambda times k squared plus lambda squared pi r squared minus 2 pi lambda rk. If this is positive, then there is a temptation. Note though that cheating outcome assumes that the private agents are systematically deceived into maintaining lower inflation expectations. Obviously, if there is a cheating in one period, then this is going to affect the expectations of the private agents. And this effect on these expectations is something that we call the cost of cheating. So there is a temptation, but there is also a cost, which is the loss of reputation. This cost we can define as punishment. Obviously, the rule can only be credible if the cost of cheating is balanced with the temptation of cheating, or if punishment is balanced with temptation. Now we have to look at the cost associated with the loss of reputation. And we can do this because this is a repeated game. We're over the infinite time horizon. So in every period there is some measurement from the previous period where the behavior was as announced. So imagine the case of the policymaker having cheated in period t minus 1. Obviously the public are now going to realign their expectations given the fact that the policymaker cheated in the previous period. This cost from the policymaker cheating is the increase in the inflation expectations for the private agents. So we have this trigger which acts as an enforcement mechanism, which is reputation. If the policymaker behaves as expected, in line with the fixed rule, then inflation expectations will be in line with the fixed rule, i.e. pi e will be equal to pi r. But if the policymaker cheats, then expectations adjust in the following period. So we have that the pi e becomes pi d, in other words, inflation under discretion. So there is some increase in inflation expectations, and we know that that is costly to the economy. So this trigger of the change in expectations acts as an explicit reputation mechanism. So long as the policymaker behaves as announced, expected inflation will be equal to 0, but otherwise, if there's any misbehavior, then the agents will expect higher inflation, this k over lambda, this inflation bias. In other words, the cost of cheating today is to unhinge inflation expectations tomorrow and cause a cost. The policymaker gives in the previous period, the public come to expect discretion, and this changes the expected loss. So the cost of cheating, something we can define as the punishment, is the difference, the discounted difference, between the expected loss under discretion and the expected loss under the fixed rule. And we can write that mathematically. The punishment of cheating is equal to the expected loss under discretion discounted by 1 plus r minus the expected loss under fixed rule, 1 plus r. And if this is higher, if expected loss under discretion is higher than expected loss under the fixed rule, then there's a positive punishment, and we can see that that would be the case. Now we can write this punishment function more explicitly as p pi r equal to 1 over 1 plus r, that's the discount, times k squared over 2 lambda minus lambda pi r squared divided by 2. So the punishment refers to the present value loss of the transgressions in inflation by the policymaker. Now we look at equilibrium. Something else we have to consider is that when the public are forming expectations in the first place, they are aware there is an incentive for the policymaker. They're aware of the temptation function. So obviously the system has to be set up so that the temptation is lower than the punishment, and we'll look at that in more detail. If the discretionary equilibrium prevails, in other words, if the private agents are expecting cheating right from the beginning, and this raises the question, under which conditions could the rule become a sustainable monetary policy regime? Sustainable in that it is credible from the beginning. Well, we've almost worked it out already. We know there is a condition that the punishment of reneging, cheating, has to be greater than the temptation, and then the private agents will believe that the policymaker will not cheat. So this is a condition that ensures equilibrium, that T of pi r, the temptation from cheating, has to be less than or equal to the punishment from cheating. So rules that can satisfy that enforceability condition can also apply in equilibrium. In fact, there are many inflation rules that satisfy that enforceability condition, but one that minimizes the expected loss the most is the one for which temptation is exactly equal to the punishment. And we can write that by making those two functions equal to one another and solving for pi r, okay, the best enforceable rule, pi r, is equal to k over lambda times 1 minus phi divided by 1 plus phi, where phi is some collection of parameters, i.e. the policy parameter lambda and the interest rate r. Notice now that inflation is also dependent on the discount rate r, and that the higher r is, the closer inflation will be to that under pure discretion. And let's look at that. The higher r, we can see r is on the denominator of phi, the lower phi will be. In fact, if it's high enough, phi can be close to 0, which will make this term, this part of the rule on the right hand side, close to 1. If this is close to 1, then pi star r will be just k over lambda, which is the same as the case of discretion. So by imposing a cost of cheating, we have a rule that delivers inflation that's lower than under discretion. So what have we learnt on this course so far? Well, in lecture 1 we learnt that including expectations gives us better macro models. From lecture 2 we learned that to solve rational expectations model, and from lecture 3 we learned to analyse and criticise the rational expectations model and discuss the solutions to these models. In lecture 4 we looked at ways of accounting for inertia we see in the data, the smoothness that we see in price data, and we used rational expectations to develop a forward-looking model called the New Keynesian-Phillips curve. We've also learned from the lectures 5, 6 and 7 that in terms of monetary policy, it's actually better to commit and then cheat unless we care about our reputation. So the optimal income in one period is to cheat after committing.